What's up, everybody? How you guys doing? Terrible. Thanks for asking. This week, I'm getting back to basics with a good old soldering with poor descriptions on what I'm making and how it works video. You know, I basically started the channel because I wanted to share my journey on learning electronics and, well, making shit. And to be honest, I let that get away from me for a little while there. I was worrying too much about video analytics and growing the channel, and not about what I was actually doing and learning. I have projects sitting around for months because I was still learning on how to get that audio and video quality up to some sort of decency. Remember, I'm just some old dude in the basement who bought a copy of Final Cut Pro. Yeah, I'm a Mac guy. Shoot me. Well, I think I got the audio down. You tell me. As for the video, well, that was always the easy part. Just cut out the dead parts and speed it up. Anyway, just a little ramble. I hope you guys enjoy this one. As always, let's check that everything's here. And here's a list of tools we're going to use. And with that, let's get to making shit. So I found this kit on eBay. You can pick it up now for like $12. I think I paid $25. Whatever, man. I'm always getting robbed. As you saw, this thing came with absolutely no instructions whatsoever. It's just a bunch of parts and a PCB. But let's be realistic here. Most of these kits' instructions are, well, how do I put this nicely? They suck. Yeah, that's the phrase. They suck. But this one, not even a content list or a thanks for purchasing. Oh well, -1 shit, you random seller on eBay. Anywho, they get back that -1 because the PCB itself is meticulously marked. Every place on the board is marked with its component's rating, 1K for the resistor, or the number of the chip. I think I like it better without the instructions. It's weirdly easier. And I don't need a translator. So as always, I like to get the small components out of the way first. Well, I guess they're all small components, but you get what I mean. So going in first are the resistors. Lots of them. First up are the 1000 ohm resistors. These are there to control the flow of current and make sure that those 7-segment LED displays don't burn out. There's 47 of them. One for each segment on each of those 6 displays. As for the soldering, I'm keeping it around my normal 712 degrees freedom height. It's just a number I chose. I don't know why, but it works for me. And can we all agree Fahrenheit is better than Celsius? Enough with all the fighting. Look, man, Fahrenheit over Celsius for temperature, and metric over imperial for measuring. I'll fight you, bro. Now it's time for fun with magnets. Catch those cut leads with a magnet, and no more mess. Or just cut it over a box. Either or. And don't forget to keep that board clean. Nothing like no clean flux. Now one of these days, I'm going to learn those codes on those resistors. But honestly, it's just easier to check them with a meter. Huh. I wonder if you took a picture of it and put it in Google, if it would just tell you what it was. Okay, I tried it. It does not. But ChatGPT does. Kind of. It did notice one of the bands, but once corrected, it worked fine. So yeah, still easier to use a meter. The rest of those resistors, well, they're going to help with the setting of the timing in some of those chips, along with the caps that are coming up. The resistor is going to set the speed of how fast those caps discharge, and in turn, will set the timing. Now for the diodes. They are responsible for keeping that current flowing in one direction. No backfeeds on this board. And in other news, they're also responsible for making sure that the signals are only passed when certain conditions are met, like in this case when 59 seconds turns over to a minute, or 59 minutes to an hour. It's going to let that signal through and tell the other chips to change the numbers. And remember, diodes are polarity sensitive. There's a line on the board which should line up with the stripe on the diode. Those red LEDs, well, they're your colons to separate hours and minutes. The resistors next to them are of course controlling their current so they don't burn out. I guess 1 or 2 of those IC chips is controlling them, but no diagram. The trace is going to one of the outputs though, so yeah. Next are the caps. The little small brownish ones are 30 picofarad and they're part of the oscillator circuit. They're working with that 32,768 Hz crystal oscillator to ensure that it stays stable and accurate. This is a must. If that oscillator drifts even in the slightest, you're going to lose a game time and have a really shitty clock. The yellow caps, the 103s, and the large 100 UF cap, they're there for your voltage smoothing, stabilizing frequency, and filtering noise from the power supply. They keep everything running smooth, though The larger electrolytic cap is also polarity sensitive. Gray stripe to the white side of the PCB. Now for the 7-segment LED displays. There's 6 of them, obviously. Seconds, minutes, hours. You know, it's a clock. Each of these segments needs a signal to illuminate. There's 10 pins to each of these. 7 for the number, 1 for the decimal point, though it looks like in this application that's not being used, as we have colons, and a power and a ground. They're your basic numeric display devices. I'll give a better explanation on how they work when I get to the IC chips, but I'm still writing this, so we'll see. Keep that board clean. Trim those leads. Wash that no-clean flux away with IPA. So going in now are the IC chip sockets. These hold the IC chips in, like cradles. I used to never use these as they make the board, in my opinion, look amateurish. But of course, this has come back to bite me in the ass numerous times. So here they are in all their glory. Now after installing these, I installed 2 switches and power jack. We all know what those are. So I'm going to spend the next few minutes going over what those chips do and how they work. Now let's dive into those IC chips. I mean, they are the brains of this operation. They deserve lots of love. There are 12 chips in total. 4 are CD4511BEs, 2 4518s, 2 4060s, and 1 4013BF. What do all those numbers mean? I have no idea. But let's start on their adventure on how they make this clock tick. Yeah, I know. So let's start at the beginning of this circuit. The CD4060 is a 14-stage binary frequency divider and oscillator. The chip generates a pulse that drives the entire clock. The 4060 is powered by an external crystal oscillator, and in combination with those caps and resistors we installed before, it divides that crystal oscillator's 32,000 something frequency down in steps to 2 Hz. Now you may be thinking, why not just use a slower crystal oscillator? And to that I say,
good question, Aguado.
I was thinking the same thing myself. Well, doing a little homework, ChatGPT, this is what I found. One reason is power efficiency. 32,768 is a very low frequency, and using a crystal at this frequency helps minimize power consumption. Another is 32,768 is a power of 2. The 4060 frequency divider is a binary divider, which works efficiently with frequencies that are powers of 2. Dividing 32,768 kHz down to 2 Hz involves 14 binary divisions. I did the math. It checks out. 32,768 divided in half, 14 times, is 2.
Nerd!
Also, these crystals are industry standard, due to them being extremely stable and accurate. Now, moving on to the next chip, which is the 4013. This is a dual flip-flop IC chip. It's responsible for dividing that 2 Hz frequency in half, again, to 1. Now, why not just use another 4060 instead? Again.
Good question, Aguado.
That's what I thought. The 4013 dual flip-flop is essential for the clock's counting and timing. It helps divide the frequency from the 4060 into precise time increments by toggling its output on each clock pulse. This allows the clock to accurately track seconds, minutes, and hours, reset when needed, and ensure smooth transitions like rolling from 59 seconds to 00. Without it, the timekeeping wouldn't be as precise or reliable. So, from my understanding of this, the 4060 handles the frequency divisions down to 2, and then the 4013 takes that frequency and makes it digital, either 0 or 1, and more accurate. I think. I don't know, man. I'm just some dude in the basement. Next in the chain is the 4518. This is a binary coded decimal counter. It counts from 0 to 9 for the seconds, minutes, and hours. It works with the 4013 flip-flop to increment the count. The 4013 receives a clock signal from the frequency divider, and each time it toggles, it sends a pulse to the 4518. When the 4518 counts to 9, it rolls over and triggers the next counter. This interaction ensures accurate timekeeping, allowing the seconds, minutes, and hours to increment properly, and reset at the right intervals. Okay, now that we have time figured out, we move on to how we get it to the displays. And that's why there's 6 of these chips. The CD4511 is a binary coded decimal to 7-segment decoder driver. Yep, this chip was specifically designed to decode BCDs and convert them into signals that control a 7-segment display. It takes the 4-bit BCD value, 0 to 9, from the counter and activates the appropriate segments on the display by lighting up the right segments for each number. It does this by turning on or off the LEDs in the 7-segment display based on the binary code it receives. This enables the clock to visually show the current time, whether it's seconds, minutes, or hours. Oh, hey, and if you're following along, make sure that you put those chips in properly. The crescent cutout should all match up on the sockets and the PCB. So would you look at that? We just built a digital clock. Well, I did. You kind of just watched. So let's get power to this thing and try it out. Place your bets. Did I get it right on the first shot? Even if I didn't know, I would say no. There are a lot of components in this thing, and I had to miss something. But hey, what's the saying? There is no better teacher than failure. So I'm going to be honest here. I have no idea what I'm doing. I made this clock months ago. I think it was mainly because I didn't know what the switch did. It stops time, basically. It's a time stopper. But as you'll see, there are problems. Well, it's one problem. I'll save you me trying to figure it out, and I'll just fix it and tell you how I did it. So yeah, stupidity. That was the problem. I put one of the diodes in backwards, so it wouldn't send that signal to the minute to the minute. How would you explain that? To the minute segment? Yeah, alright, the minute segment. So it wouldn't send the signal to that minute segment to roll over to the next minute. Oh well, like I always say, if I wasn't so dumb, I'd be smart. Smart. That's a weird word. It's like a word a dummy came up with because they didn't know the word intelligent. It's like, I'm smart, Mikey. I'm smart. Oh man, where was I? Don't mind me, I ramble. So I fixed that by flipping the diode around. I just desoldered it with some wick and a solder sucker, and that was it. So, let's see if my repair was successful. Wait for it. There it is. Look at that. A functioning clock. Well, that only took 2 hours. So, 2 hours to put together and 15 minutes to figure out where I messed up. Not a bad night. All in all, I really like this one. Not having a diagram was a bummer, and I really did overpay for it considering you can get it for $12 now. Oh well, I'll leave a link in the description if anyone wants to pick one up. And I hope my explanation on how these components work together wasn't too bad. I mean, I came into this not knowing how any of these chips worked, and I feel I leave with a good grasp on it. And I hope you do too. As for a rating, I'm feeling pretty generous. It was a fun kit to put together, and I think this video just made it all the better. 4 shits. And with that, I'm out of here. Here's some sexy B-roll, and as always, thanks for watching.